Welcome back to another great section of this great tutorial class. Today we are going to be looking at application of dimensional analysis of physics. You know, in our last class we looked at how to solve or to calculate the dimensions of physical quantities in physics. But today we are going to be looking at how to apply them. Now, in a nutshell, we can use dimensionals to check whether a particular equation is valid. Taking of that, we need to test for the validity of an equation or the consistency of an equation, or to check whether a particular equation is correct. Then we also use dimensional analysis to solve for units of physical quantities. Then we also use to provide partial or potential solutions to problems whose direct solution cannot be achieved by a stated method. That is, we use dimensional analysis to solve or derive equations or establish formulas. But for this class, we are just going to be looking at how to use dimensional analysis to test for the validity of an equation, or to check whether a particular equation is valid, or the consistency, or how to know whether a particular equation is correct. So please, in this class, ensure you don't distract yourself. And very important, you know you are not subscribed to this channel, please try and do so. You know we are blessing you with so much knowledge. What you have to do for us now is just for you to subscribe. Subscription is free. What you have to do is to click on that subscription button. If you know you are not registered with YouTube, just register with validity. That is all. You don't have to spend any money on that. So please try and subscribe to this channel. So look at the first question we're having for today, which is you take down. If the power developed by a moving body, is defined by the equation P is equal to force times velocity. Is defined by the equation P is equal to force times velocity. Use dimension analysis to check if this definition is correct, or if this equation is correct or valid. He said the power developed by a moving body is given as P is equal to force times velocity. Use dimension analysis to check if this equation is correct. So let's check whether the equation is actually correct. Now, look at what you do. If you want to check whether a particular equation is correct from dimensional analysis, it's a very simple thing. What you have to do is you have to know the dimension of each of the physical quantity present in that equation. Remember, we have P is equals to F force times something like this. Power is equals to force times velocity. Now this one is not pressure, this one is power, this one is force, this one is velocity. So what you have to do, you must know the dimension of this, and this. Then, at the end of the day, you will simplify both left hand side and right hand side to check if the dimension of both sides will be the same at the end. Now, if you have simplified this left hand side and you simplify this right hand side, and at the end of the day, the dimension of both sides are not the same, you say yes, the equation is correct. If they are not the same thing, it means the equation is not correct or not valid. That is how it is. Simple as that. Look at what I'm trying to say. You say, okay, what is the dimension for power? Remember, in our last class, or if you want to check for the dimension of physical quantities, power is just, the dimension of power is m L squared raised to power minus 3. That's this dimension of power. But it's equal to what dimension of force? If you don't know how to calculate the dimension of power, force, and velocity, go back to our last class, or our first class in this physics. That is how to calculate the dimension of physical quantities. Is there. Just try and look at it. What I have to do, you also find the formula. Formula of power is work done over time from there you derive the dimension. What is the dimension for force? M LT raised to power minus 2. Now what is the dimension of velocity? LT raised to power minus 1. The next thing, we have M L squared raised to power minus 3 equal to M. L times M will have L squared. Then T raised to power minus 2 times T raised to power minus 1, that will be, you pick one of the base, they add up to power minus 2, plus minus 1. So that at the end of the day, we'll be having something like this. M L squared 3 to the power minus 3 is equals to M L squared 2 to the power plus times minus will give us minus 1. Plus times minus will give us minus. Think of that. Plus times plus equals to plus. Plus times minus equals to minus. Minus times plus is equals to minus. Minus times minus equals to plus. Think of those things, very important. So this plus minus will give us minus. So another day, let's go. We'll be having M L squared 2 to the power minus 3 is equals to M L squared 2 to the power minus 2 minus 1 will give us minus 3. So let's say we have them L squared 2 to the power minus 3 to the power minus 3. The equation is correct or is what? It's valid. It's valid. It's actually valid. It's valid. So the definition is absolutely correct. Power can be said to be force times velocity. Is correct. It's very, very correct. So this is how we run these stops. So let's look at another important question. Before we look at other examples. By adding more examples, you understand it better. Let's look at another example. Remember, the first is to bring out all their dimensions. The next is to simplify. Use the rules of mathematics, like each other use the rules of indices. You have it to be valid. Now let's look at this one. Let's look at. You take this question now, question 2. Question 2. Now, if the work done developed by an ideal gas, if the work done developed by an ideal gas, is defined by the relation W is equals to PV. Is defined by the equation W is equals to PV. W is equals to PV, where W is equals to work done. Where W is equals to work done, and P is equals to pressure, then V is equals to volume. Use dimension analysis to check if this equation is correct. Use dimension analysis to check if this equation is what? Is correct. W is equal to PV. Use dimension analysis to check if this particular equation we're talking about, or definition or distribution, is correct or valid. So let's check if it's correct. Remember this word, pressure, velocity. Now, let's go. Now, what is the dimension for pressure? What is the dimension for work? What is the dimension for velocity? What is M L squared 3 to the power minus 2? Pressure is actually M L to the power minus 1 to the power minus 2. Well, I'll show you how to get this one now, in case you have forgotten. Remember, pressure is force over area. Don't forget that. There is volume. Now look at it too. W is work done. P is pressure. Then V is volume. Think of that one. Work done, pressure, volume. So what is the dimension of volume? L is power 3. So this one is actually trying to. Then we have M all squared 3 to the power minus 2 is equals to what is the dimension of force? M L 3 to the power minus 2. We have M L T raised to the power minus 2 over what is the dimension of area? L squared times L cube. So next we're going to do, we can just say, because you can just say the 2 here, don't remove the 2 from that, so you wouldn't want to be left there. And just do that, you see that it's still very, very correct. Now I want to solve out the dimension of pressure so that you see it. That's how I'll just do the next one. Remember any number that is not this way to power 1. Remember that. We have M L squared 3 power minus 2 is equals to M. Now we have L power 1, 3 power 2. What happened there? Look at what happened. This 2 will cross this division line. We don't have this other power there, but we change sign. So the 2 was positive 2 before. Because any number around sign is positive. So if it's positive, we check to negative 2. So we are going to have negative 2. So we're going to mean this 1 there because they have the same base. Think of that. Then 2 raised to the power minus 2 times L3. Then we have M. L squared raised to the power minus 2 is equals to M. L. Now 1 minus 2, that gives us minus 1. This one minus 2 times L3. So you see, this is what I have to prove that. The actual pressure is M L raised to the power minus 1, 3 raised to the power minus 2. You can see this one volume, this one pressure. I can just say 2 here and 2. 2 here, 1, 2 here, they will have 1. So just this one cancel 2 out of this, so they won't be left out. So you are using 1 to apply to have MS squared 2 minus 2. It will be valid as well. So we can see this like this. We are not going to have M L squared 3 minus 2 equal to, now we have M, that's M. Then L raised to minus 1 times L raised to 2 plus L raised to minus 1 plus 3. Pick one of the base and add on the power. If you have two numbers, let's say we have A raised to power n times B raised to power n times A raised to power n. The two bases, if they are the same thing, base and base, they are the same. Pick one of the base and you add up their power. That's how we do it in indices. Same thing. Pick one of the base, add up the power. They will have 2 raised to power. We have 2 raised to power minus 2. So we'll be having n L squared 2 raised to power minus 2 is equal to n. Now minus 1 plus 3, 2. This one minus 2. So this is what I'm going to have. Let's check m, n, L squared, 2 raised to minus 2, 3 raised to minus 2. The equation is valid. The equation is what? It's valid. To see this one is also valid. So if you have to be very fast, you have to direction of work done, you have this one pressure, volume. Then simplify everything. Before you know it, in 2 lines, you're already having your answer. So let me look at another important example. Very good example so that you see what I'm actually talking about. So this one is still valid. That is still valid. Now let's look at another example. Another good example. Now let's example 3 now. Example 3 now. Example 3. Now, if the velocity of sound in any medium, take note of this one. Write on that. If the velocity of sound in any medium is given by the equation V is equals to the square root of E over rho. V is equals to the square root of E over rho. Where V is equals to velocity, E is equals to Young's modulus. E is equals to Young's modulus, and rho is equals to density. And rho is equals to density. V is equals to velocity. Then this E is equals to Young's modulus. Then rho is equals to density. Use dimensional analysis to check if the equation is valid or correct. Use dimensional analysis to check if the equation is valid or correct. Now let's check if it is valid. Now we already know that the dimension of velocity, let's get that dimension. Velocity is Lt raised to power minus 1. Then for Young's modulus, what will be the dimension? Young's modulus has the same dimension as pressure and as stress. Stress, pressure, and Young's modulus has the same dimension. Take note of that. So remember the dimension for pressure was Young's modulus is stress over strain. Is stress over strain. So strain is dimensionless. And stress is force over area. You can also get the dimension out. So that will give us M L raised to power minus 1, raised to power minus 2. That will be the dimension for Young's modulus, the same thing as pressure and stress. Then density, which is rho, has the dimension of M L raised to power minus 3. That is the dimension for density. Now, how are we going to check whether this equation is valid or not? Place their respective dimension anywhere you see them, or just replace VE and rho in their respective dimensions. Just substitute. Let's see, we are going to have. Right, we are going to have V is LT raised to the power minus 1. Then the square root of our E is M raised to the power minus 1 raised to the power minus 2. Then over rho is M raised to the power minus 2. This will cancel this. So we'll be having the square root of L raised to the power minus 1 raised to the power minus 2 over L raised to the power minus 3. The next thing we'll be having the square root of, now we have L raised to the power minus 1, L raised to the power minus 3. Then this minus this is the same base, so we want the top side. Then remember it's already minus 1. Now if this minus is plus this division line, we change sign. Remember the first one we did. Then we check for minus plus 3 because it's crossing this division line. Then the CS power minus 2. Then we'll be having the square root of L raised to the power minus 1 plus 3, that is 2. So this power minus 2. So next we will have L raised to the power minus 1 equal to. Now remember, or if you cannot remember, then note that down like this, we have A raised to the power 1 over n, set as the nth root of A. So what is the square root of A? Set as A raised to the power 1 over 2. What is the cube root of A? A raised to the power 1 over t from indices. So nth root of A means A raised to the power 1 over n. That means square root now give you 1 over 2 because there's supposed to be 3 here, we don't use to put it. We use to put from 3 and above. So the cube root of A will be A raised to the power 1 over t. Take note of that. So since we are having the square root of this now, we can call it L squared t raised to the power minus 2. Then I this with 1 over 2. Raised to the power 1 over 2. Because this and this, I said, if you have the square root, anything raised to the power 1 over 2 means square root of that thing. Please take note of that. It's still very, very important. So next, this 1 over 2 multiply this power and this power. We just use to open this bracket. We'll be having L raised to the power minus 1 equals to L squared times 1 over 2. The raised to the power minus 2 times 1 over 2. We'll be having L raised to the power minus 1 equals to these two cancels to have L raised to the power 1. The raised to the power cancel this 1. Minus times 1 equals to minus 1. So at the end of the day, I'm going to be having LT raised to the power minus 1 equal to LT raised to the power minus 1. See? Both of them are the same thing at the end. So this shows that the value is valid. Is what? It's valid. The equation is valid. So this particular equation is also valid. Then let's look at another one, number 4. Let's take a look at another question. Number 4. That's all. If the time taken for a body to displace, if the time taken for a body to cover a displacement of D, to cover a displacement of D, having an acceleration of A, if the time taken for a body to cover a displacement of D, having an acceleration of A, is given by T is equals to the square root of 2D over A. Given by T is equals to the square root of 2D over A. Check if the equation is correct or valid. Check what? If this particular equation is what? Correct or valid. Let's check. What is the measure of time? Not the measure of everything. The measure of time is T. What is the dimension of displacement? Acceleration is LT raised to the power minus 2. So if I cancel B, that will cancel L. We are having 2 L over T raised to the power minus 2. Let's check. If I bring this 2, okay, this T raised to the power minus 2 upward, let me say, and I'm going to bring this 2 to the upper side. This power will also change sign. This is why I don't take any power because there's no T already. See, there's no T already. You don't bring everything upward. The power will change sign. For minus what? Plus 2. Then square root. So the next thing, we have T to be equal to the square root of 2 times the square root of 2 raised to power 2. So I'll cancel this. Then we will be root 2 t. That is root 2 times t. So we're having the final answer will be t is equals to root 2 times t. This one is root 2, this one is t. Now check if this equation actually valid. Now, when we are talking about dimension, we are talking about actually not like the units. Is units correct? Are they having the same what will I call it? I'll call it, are they having the same variables or physical quantities? The same physical quantity we have here, the same thing as the one we have on this side. Let's check. Is root 2 a physical quantity? No. Root 2 is not a physical quantity. Root 2 is a constant number. The square root of 2 is a constant number, which is dimensionless. So, constant numbers like this don't affect dimension. Take a look at that one. Since we have t here and we have t here, you will just assume this root 2 don't exist in terms of dimension. That is what exist. So you want to. So about is a constant number. Let's say 1 million, 100, 10, 50. About is a constant number. You assume that this one does not exist in dimension. So t the same thing. So whether we have root 2 here, that's what our business. The equation is still valid. The equation is valid. It's valid. Dimensional is the same thing. It's correct. Then let's go number 5. Let's go number 5. The displacement of a particle, is defined by the equation d equals to a over t squared. By d equals to a over t squared. A over t squared. Use dimension analysis to check if the equation is correct. Use dimension analysis to check what? The equation is correct. Let's check if the equation is correct. Let's check. When I know what the displacement L, as mentioned is L t raised to power minus 2. This one is t raised to power 2. Raised to power 2. Then the next thing I do have will be, let's check what I do have. We'll be having L is equals to LT minus 2. If this 2 crosses this line, we check to minus 2 again. Remember, if plus 2 crosses this line, we check to minus 2. So we go and let TT, they have the same base. So this will go and be this or that 2. But if it crosses that line, we change this sign from positive to negative. Think of that. And from negative to positive. We will be having LT raised to power what? LT raised to power minus 4. So we have L is equals to LT raised to power minus 4. What we have here and what we have here are not the same thing. So automatically, or you can say that this one is not valid. The equation is not correct. It's not valid. So this equation is not correct. It's not valid. So this equation that doesn't exist. It's not valid. So let's get number 6. This is the last example. Number 6. If the power develops, by a moving body, is defined by P equals to AT squared over V. P is equal to AT squared over V, where P is equal to power, A is equal to acceleration, T is equal to time, and V is equal to velocity. V is equal to velocity. Use dimension analysis to check if this equation is correct or valid. Use dimension analysis to check if this equation is what? Correct or valid. Now let's check. Dimension of power is L square raised to power minus 3. Dimension for acceleration is L raised to power minus 2. Dimension for time is T, and that is having square. Number is L raised to power minus 1. Let's use for minus 1 dimension for velocity. So that at the end of the day we'll be having is to go with this. We have m L squared 3 raised to the power minus 3 equals to, now 3 raised to the power minus 2 times 3 raised to the power 2. That was 3 raised to the power minus 2 plus 2. Add up the power. Then, if this 3 raised to the power minus 1, if this t raised to the power minus 1 moves up, we change to t. Okay, let us do this rule. I don't know if you can do everything at once. Okay, we change to t raised to the power 1. No, that one. If this one moves up, everything here moves up. You can just say, let it go and make this one, you still have the same answer. If you do it like this, let's say this and this, we're going to be added the power. Then this minus 1, go and meet any of these, you still be plus. You have the same answer, it doesn't have to be the same thing. Or, you just say, if everything here moves up, all these things around moves up, the power changes to plus 1. Remember that. Therefore, we'll be having m squared t raised to the power minus 3 to be equal to t raised to the power 0 times t raised to the power 1. That will be m all squared t raised to the power minus 3 equal to 1 times t is equal to t. This and this are not the same. This one is not, that's not valid. That's not valid. So let's have one more question before we go, please. Sorry. One more question before we go. One more question before we go. One more question before we call it before we call it. It's very, very important. One more question before we call it today. Now, if the work done of a body is defined by the formula, or the relation, this is test number 7, by relation, W is equals to M times D over T. M times D over T. M times D over T. Whenever you use work done, M is momentum. Now it's new. M is momentum. D is distance moved. And T is time. Whenever we use work done, M is momentum. D is distance moved. And T is time. Check if the equation is correct. Check if the equation is what? Is correct. And let's check. If it is correct. Let's check if it is correct. Let's check if it is correct. We have W. Yeah, what is the dimension of W? Look at all their dimensions. The number of the W is M L squared raised to the power minus 2. What is the dimension for momentum? Let's say we don't know it. What is the dimension for momentum? Momentum is actually a product of mass and velocity. That is mass times velocity. That is momentum. And times distance now. Then divided by time. So that's what we have now. Mass times velocity times distance. That is momentum. Momentum is mass. Momentum is mass times velocity. That is the definition of momentum. So we have it m L squared t raised to the power minus 2 to be equal to what dimension of m? Velocity is L t raised to the power minus 1. Distance is L. Then time is t raised to the power 1. So if this one, probably this division has to go and make this one. That one will change to negative 1. We are going to have m L squared t raised to the power minus 2. MS squared t raised to the power minus 2. Then equal to m L times L half L squared t raised to the power. Then if this one here, you can move everything up, there's no need. You already have t here. You move this one, you go and move this other one here. But this one will change to minus. You have minus 1 first. This other one will go and meet it and change to minus 1. But it's not the division line. Then we'll be having m L squared t raised to the power minus 2 to be equal to m L squared t raised to the power minus 2. So let's check L squared t raised to the power minus 2. Basically, dimensionally, the equation is valid. Equation is actually valid. So let me give you one to do as assignment. Ensure you do it. Ensure you do it. So that will be supposed to be question 8, but you do it as assignment. That will be assignment. Assignment. So are you ready to work? Okay. If the force exerted on an object, if the force exerted on an object or on a body, if the force exerted on a body, if the force exerted on a body is given by the formula F is equals to P times V over D. P times V over D. Please listen to me. Listen carefully. You know it's force equal to P times V over D. So look at the definition of F, P, V, and D now, so that you can be able to solve it. Where F is force, P is pressure. P is pressure. Then V is volume. V is volume. Are you there? Then D is distance. D is distance, volume, pressure, and force. So check if this equation is correct or valid. So check if the equation is correct or valid. And the answer we are going to have will be